In this video, I'm going to demonstrate how you can utilize AMOS graphical user interface in order to carry out a basic regression analysis and path analysis. Okay, so first off, let me just introduce you to the graphical user interface. This is what it's going to look like. Basically, you can see that the interface has essentially a drawing area right here where you can draw out a structural equation model. So you can utilize the rectangles or boxes in order to draw out observed variables. You can use ovals in order to draw out latent variables. You can also use arrows and double-headed arrows in order to draw out the relationships among the variables in the model. So you can also use this little X right here in order to erase objects if you just click on them. So at any rate, what I'm going to do is start off by illustrating how you can import data into the AMOS program. So we will start by looking at some data, a data file in SPSS. So this is an SAV file in SPSS. The file has 50 cases involved and basically 4 measured variables. So we have subject matter interest, mastery goals, anxiety, and achievement. And so we want to import this data set into AMOS and run our analysis. Keep in mind that AMOS is basically an add-on to SPSS, but you still have to import the data from SPSS into the AMOS program. So I'm going to click back onto the AMOS icon, and to import data we'll go to Select Data Files. So we'll click on that, and under File Name we'll click on it, and you'll see down here you've got a little tab where you could actually select different types of data files. So you've got IBM SPSS, text file, you've got Excel files, and so forth. So we're going to stick with the AMOS file right now. And so we'll click on this button right here and then click on Open. When you click on Open, you'll notice the name of that file appears here under File, and you've got the N, which is the number of cases in that data file. So we'll click on OK. And so at this point, we'll know if the data file actually was imported. If we can just click on this little button right here for List Variables, you'll see that the variables that were in our original data file are now, the SPSS file, are now imported into AMOS. So let's start by drawing out a basic regression model. So keep in mind that conventional SEM drawing entails the use of boxes or rectangles or ovals or circles. So we're going to draw out our measured variables in the model. It's going to be a standard regression analysis. So we're going to draw out a box here. We can draw out a box down below and draw another box down here. And there's our dependent variable. Now you can see it's not great looking. If I want to have boxes of equal shapes, what I could do is to make life a little simpler is just go over to this little button and click on it where it says duplicate objects, and you can see now my cursor has the icon for a copier, and so I can just click and drag, and so now the boxes appear below and it's in the same dimensions as the one we started with. So there you go. So now I'm going to click off of this to remove that, and I can draw arrows and direct effects in my model just by clicking on the little arrow button. And so now when I bring my cursor over, you can see the little arrow up here. So I'm going to draw out this right here, and you can see it starts with red, then goes to green over here. And that's how you know you've included the effect all the way. Otherwise, if you don't go all the way, then it'll disappear on you. So you need to draw all the way over. There you go. So now I want to click on this button right here to create covariances among the exogenous variables. An exogenous variable in the context of SEM terminology is a variable that does not have any predictor variables associated with it. An endogenous variable, which is this one right here, has basically arrows pointing to it, and it's a variable that is being predicted by other variables in the model. So I'm going to click off of this, and so when you have an endogenous variable, the endogenous variable has to have an error term. Basically, in the context of a regression or path analysis, the error term is called a residual, or another term for it is a disturbance. So I can either draw out a disturbance term, or I can just click on this little button right here and go over to the box and click, and so now you have essentially a figure for the disturbance term. So I'm going to click off, and so now I can put in the names of my respective variables. So I'm going to click on this little box right here, and now I can just click and drag my variables over into my boxes. There we go. So now, and so basically what's going to happen is when I run the analysis, the data associated with these variables are now included. Now with the disturbance term, what I have to do is I have to give this a name. So what I will do is I will right click and click on Object Properties, and I can just call it a variable name. I might just call it D for disturbance, or E for error, or R for residual. I'm just going to call it D for disturbance. And then click out of the box. Now, if I wanted to change the names that appears in the boxes in my figure, I could do that by clicking on Object Properties, or I should say labels. The variable name is what is in the actual data file. So we don't want to change that, but under label we can change the label that appears in the figure. Like for instance, if I wanted to call it subject matter interest, I could do that, and I can even do things like adding in a break and so forth, and so it looks like this. If I want to click on master goal and change this, I could say mastery goal, and so forth. So I can do that pretty easily as well. So those are some options there if I want to do that. I don't have to do it, but that's an option if I want to, if I want more description or something like that. You can also change the font size of the label, or if the name's appearing, change that as well. All right, so I'm going to click out of this to run the basic model. And like I said, with the D right here, you have to we're going to give it a variable name D, so you don't really have to create a label down here. We'll just keep, so this is where some of the logic departs a bit, in that the variable names with your measured variables come from the data set, and then you can add a label and change things here. But in the context of this latent variable right here, you just give it a variable name. All right, so to specify the model, I'm going to go to Analysis Properties, and this box will pop up, and you've got several options for estimation of model parameters. So there's maximum likelihood, least squares, generalized least squares, unweighted least squares, and so forth. Generally, in most SEM applications, folks with the maximum likelihood estimation. The unweighted least squares would just be a negative to the standard model regression least squares analysis that you would have in the context of SEM, in the context of SPSS. So at any rate, we're going to stick with maximum likelihood estimation. If we want various outputs, we can click on this button right here. We can ask standardized estimates. Otherwise, we'll get the unstandardized estimates, and that would leave us with unstandardized regression coefficients and covariances among the exogenous variables. So if we want to add in standardized estimates, which would be basically the beta coefficients and correlations among the exogenous variables, we can click on this button. We can also ask for the squared model correlation for the model, which would basically be the R-squared value for indicating the proportion of variance accounted for by the predictors. And there are other options as well that we're not going to get into in this particular illustration. I guess we could test for normality and outliers if we want to look at that. All right, so we're going to click out of this, and now to run the model, we're going to click on Calculate Estimates. So when we click on that, this box is going to come up, and you have to give it a name, give your project a name. So I'm going to call this regression model, and you can see I was working with a previous one, so I'm going to stick with this one. and then click on Save. And so now when so actually I'm just going to save over the other one, looks like. And so now you can see up above, it says, you can't really see it very well, but it says regression model right there. So now what I'll do is I will click on Calculate Estimates again, and so now it's run the basic analysis. And so it may not look like it, but basically I can click on this little button right here. There's a little toggle between the model building portion of the interface and the estimates portion. So you can see that when we click on this view output, what you get are various estimates. You can also see that you can toggle between unstandardized and standardized estimates. So we only get these if we ask for the standardized estimates under analysis properties. So under unstandardized estimates, you can see we've got the unstandardized regression coefficients, an estimate of the variance error, or basically variation in achievement that's not accounted for by the predictors. These values right here would reflect different variances and covariances involving the predictor variables. So if we wanted to take a closer look at that, we can go under View Text, and under estimates we can see this. So you can see that these are the unstandardized regression coefficients where it's listed under regression weights, the standard errors, and a critical ratio, and then we've got our p-value. The critical ratio is just a ratio of the estimate to the standardized estimate. So p-values are given for two-tailed tests, which you see right here. So keep that in mind if you're testing a directional hypothesis. So again, these regression weights, these are unstandardized regression coefficients. Those are the things that you're seeing in the unstandardized solution. If we scroll down a bit, you can see that we've got, in terms of the variances, these are the variances of the exogenous variables in the model. So you got subject matter interest, the 24.5, the 8.82 for mastery goals, anxiety 141.12, and then the error variance associated with the disturbance term. So that's the variation in achievement not accounted for. And then the covariances are the unstandardized, essentially unstandardized correlations among the exogenous variables. So there's the 5.145, which is this relationship. The mastery goal anxiety relationship is this right here, the negative 12.35, and so forth. If we want to look at the standardized estimates, then we can click on it. And if we want to compare that to the output file right here, you'll see that basically the standardized regression weights are listed right here. So there's the 0.39 for the relationship between achievement, which is our outcome variable, and subject matter interest. The relationship between mastery goals and achievement, you can see is 0.18 right here. And anxiety and achievement is the negative 0.22 right here. If we scroll down, we can also see the squared multiple correlation, which is the R-squared value, which is the 0.35. Now, if I want to make some changes to in terms of what I see in my output file, I can do that. Like for instance, let's say I want to hide the R-squared value. I can right-click on the box and click on Object Properties, go to Visibility, and click on or click off of Show Parameters, and so it disappears. If I want to go back to standardized estimates, if I wanted to use those and clean things up a bit, I could just as easily do that. I could say click off the show parameters, and that's hidden. Or if I want to do it for each of the variances here, if I don't want to show those, I can do that. So basically by clicking on show parameters, the parameter is shown. If I click off of it, then obviously it's not shown. In terms of other outputs to look at, so all that was under the estimates. There's the assessments of normality. What you have right here are essentially these are tests of the univariate normality. You've got skewness value as well as the critical ratio, kurtosis value, and the critical ratio. So those can be handy in terms of evaluating normality. And then there's also a test of multivariate kurtosis. So we're not going to spend much time on that right now, but just to highlight that you can get that kind of information as well. Under model fit, this is pretty useless in the context of a regression analysis like we just computed. But basically, when we run path analysis and more complex types of structural equation models, then you also have indices that indicate the degree to which the overall model is fitting the data. So in addition to looking at the individual regression parameters or path coefficients in the context of a regression a path analysis or with or without latent variables, we can also look at the overall model fit. So like I said, we're not going to really focus on that right now, but just to kind of highlight that that's available in the context of more complex models. So this is just a basic regression model that we were running. I can also import data through other routes as well. I can click on the select data file right here. Like for instance, if I have my data in, let's say, an Excel file. So here's my data in an Excel file. So I've got the raw data listed out all the way down to row 51. The first row contains the variables in my analysis. So if I want to import data from Excel, what I will have to do is actually basically convert this to a previous edition of Excel, at least in this version 19 that I'm working with. I haven't really messed around with a later version, but this earlier version that I have on my computer, I basically have to convert this to a previous edition of Excel. And then when I want to run the model or import the data, I can go under File Name and then go to Excel 8.0, and so then there it is. Otherwise, like I said, it wouldn't appear. So now I'm going to click on Open, and so it's basically there. There's the Excel file. Click on OK. If I was starting a new model, let's just go back and do that, just so that you can see it. I'll just import the data using this version of Excel and just draw it out really quickly. And there's this path, and this path right here. Click on this little button right here, and I'll create my covariances. Oops. You can see that if you don't go all the way, it's not going to draw. So be sure that you do that. And I'll just draw in subject matter interest here, and mastery goals here, anxiety here, and achievement here. Create my disturbance term. Go under text and just type in, I'm just going to type in D. And so again, we've got the XLS file that's here. And analysis properties, I'll just go and click on what we had before. And so now when I click on save, or actually I can click on save, but I'll just go ahead and run it, and it'll go ahead and it'll request me to give it a name, so I'll just say regression 2. And there you go. And so now it's been imported. I've got all my estimates as before. So that's how I got the data file from Excel into AMOS. Another possibility is that I can take summary data and bring it into AMOS as well. And so summary data, for instance, might appear as follows. So let's say I go into actually, I'll just go into this select data files, click on file name, and just open this up just so you can see what it looks like. So here we've got data in a summary format, and this is laid out the same way actually in SPSS. So I've done the same thing. So you can see that basically to create the summary matrix data right here, if you go under variable view in SPSS, I've got row type with a little underscore, var name underscore, and basically the names of the variables listed here. You can see I've got these variables are given strings for the first two and then numeric values for the second two. So so I basically have the data in summary form both in SPSS and also in Excel, and so I can import these matrix summaries into AMOS and run my regression analysis or path analysis or whatever utilizing summary data. So literally I could take data out of a journal article like a correlation matrix, means and standard deviations for the variables, and also the sample sizes for my variables, and basically run an analysis through AMOS. So to illustrate what I'm talking about here, I've got the Excel data, and it's actually saved under the previous edition as well. So, you know, basically it's saved under the 95 workbook, and then so if I want to import the matrix summary data, I can just click on matrix data, open, and you can see that it's under sheet 1 right here, and so there it is. So there's the summary data. If I click on OK, now you'll see again there are my variables listed, and I'm just going to leave this model alone and just rerun it, and so you can see that the analysis was carried out using the summary data. The same would go as if I was importing data from SPSS. So I'll go down to IBM SPSS, and I'll just use this little file, matrix data for importing. Click on open, and you can see there's the data file, the ends listed, OK. And so now once again you can see there are the variable names, and just kind of go back here, and so if I click on calculate estimates, let's see, what I may need to do is just keep that open. And I actually, what I'll do is I'll just give this another name. I'll just call this regression 3, and then run. And actually, I think what the problem is that under mastery goals, I believe it in the SPSS file, I believe it had an S on the name. Yeah, it had an S on that name. Actually, I'll just get rid of that S and resave it, and then I'll just upload it as before. So in this particular case, it'll just call up. It's going to recall up that matrix data with that correction to the SPSS file. And so now when I run the analysis, it's still acting up. Okay, so I just had to go back, and I didn't just need to fix the M goal here, I also needed to fix it up here, because these are the variable names as well. So that's basically what happened. So I just resaved my SPSS file here, and we'll just re-import again. So you can see it gets a little buggy if you're not careful. So we've got everything listed in here. So now I'm going to click on calculate estimates, and now the data analysis has been run, and you can see there are the unstandardized estimates and the standardized estimates. So now let's say I want to test a path model, and let's say, for instance, I'm gonna do away with I'm gonna put I'm gonna make anxiety an endogenous variable, and have essentially I'm gonna run a path analysis with anxiety predicting achievement, but these other two variables predicting anxiety. So I'm going to click on the little moving truck right here and move this guy over a bit, and I'll draw an arrow from each of these two variables. Actually, I'll do a partial kind of mediation for mastery goals, and I'll leave just a full direct effect on achievement here. And I can add in, I've got to add in a disturbance term for all the endogenous variables, because now anxiety is being predicted by another model, another variable in the model. So I'm going to click off of here, and I'll just right click here and just call it D2, and I'll just make this one D1, so for the first disturbance. So now we've got essentially a path analysis model, okay, with using measured variables. So in this case, what I'm going to do is I'm just going to save the project as path analysis, and click on save. And under analysis properties, we'll just leave everything as before. So we'll get the standardized estimates, the squared multiple correlations, and so forth. We'll leave our tests, normality tests and outliers indicated there. We could also ask for direct and indirect effects if we wanted that. For the time being, we're going to leave that alone. And now we'll run the basic analysis. I'm going to save everything and then click on actually, one other thing that I want to mention is we can actually change the interface itself, kind of widen it out a little bit if we want to. If we go to View Interface Properties, we can actually expand the space, because you can see right now things are starting to get a little tight. If we had a lot of variables to work with, then things could get really tight really fast. So if I want to expand the drawing space, I can click on this button right here, go to Landscape, and apply, and so now it widens out, and so now we've got a much larger area to work with if we wanted to draw out if we had other variables to include in the model. A couple of other things to note too is if I wanted to move the figure, I can click on Select All Objects and then click the little moving truck here, and I can move this around. Then I can deselect if I wanted to, or if I wanted to select one piece of the model to move, I can certainly click on the little moving truck and move it around. If I wanted to click on a couple of things and move it around, I can click on these three right here if I want to keep the same orientation, and then click on the moving truck and I can move all of that around. So basically these little tools can kind of help to make, I'm going to deselect now, these tools can kind of help you in cleaning things up, particularly if you wanted to use your figure in a journal article or paper that you're presenting. So at any rate, I'm going to save this again, and now I'll click on the little Calculate Estimates button. Really quickly though, if there was any missing data in your data set, one of the things to note is that what you'll need to do is you'll need to click on Estimate Means and Intercepts. So that's an important thing if there's any missing data. This right here will produce a full information maximum likelihood estimation of the parameters, which will basically adjust everything for the presence of the missing data, and it yields pretty good estimation. If you have any missing data, that's what you're going to need to do in that case. If you want to deal with missing data prior to running your analysis and create a full data set using some type of imputation strategy or listwise deletion or whatever, you can certainly do that. Just make sure that if you're not going to click on this, make sure that you have a complete data set that you're working with. But like I said, if you do want to, if you do have missing data, then you can click on this button and then it will run. Otherwise, if you don't click and there's missing data, you'll get a little error message that says that you have to click on this button. So it's kind of funny in that respect. So in the current data set, I don't have missing data, but I'll go ahead and click on that just to illustrate my point. So I'll click on this button right here, and so now you can see, clicking on this box right here, we've got our unstandardized estimates and standardized estimates as before. So these are the R-square values in the model. So under the standardized estimates, this is the correlation between the predictors, and these would be basically beta weights as you would interpret them in the context of a regression analysis. These would be the standardized regression coefficients. Whereas if you click on unstandardized, these would all be unstandardized regression coefficients. This would be the covariance between your predictor variables, and then this would be the variance associated with your disturbance terms, and then this would be the variance accounted for, or the variation explained by the predictors. So again, if I want to right click and kind of clean things up a bit, I can certainly do that just by clicking off the show parameters right here. So you can certainly do all that very easily. If we go to, I'll click that one off too, so that kind of cleans things up a bit. So if you want to go to View Text, now under Estimates, you'll see again, these are the paths in the model. So we got basically for the unstandardized regression coefficients, you've got mastery goals to anxiety. So that's this path right here, the 0.47. Or excuse me, mastery goals to anxiety, it's the negative 1.14, which is what you see right here. And there's the p-value testing that parameter estimate. So again, these p-values are for two-tailed tests. That would be a statistically significant effect of mastery goals on anxiety. You've got subject matter interest to achievement, and so there's the unstandardized regression coefficient there, and it would be significant. Mastery goals to achievement, there's that path, and you can see that that would not be significant, nor the relationship between anxiety and achievement. That path is not significant in the model. If we kind of scroll down, there's our means for each of the variables and the intercepts for each of the endogenous variables. So there you go. The covariance between subject matter interest and mastery goals is listed right here, and the variances of our exogenous variables and the disturbance terms are listed right here. So again, if we wanted to show that, there's the show pictures right here under object parameters, object properties, visibility, show that, just to kind of demonstrate this little point. Then you can see the variances. The variance for subject matter interest is the 24.5, which you see right here. Under means, there's the mean for the before the comma right here. For the disturbance term, the 41.037 is this right here, and the mean is actually 0 for the disturbance term. If we click on standardized estimates, again, we can look at this in a little bit more detail. So in this case, we've got, if you scroll down to the standardized regression weights, these are the values that are shown in this particular model. So the relationship between mastery goals and achievement is, and anxiety is negative 0.35, which is that. Subject matter interest and achievement, it's the 0.39, which you see right there. If you scroll down, you see the correlations. The correlation between subject matter interest and mastery goals is 0.35, which is what we see right here. If we click under model fit, now we have basically an over-identified model, and basically we have enough. We have a little bit more information in the covariance matrix than is necessary in order to estimate the parameters of the model, and so we're left with 1 degree of freedom for the model. And so this is the chi-square goodness of fit test, and conventionally speaking, we're looking for a non-significant chi-square value that, and that would be indicative that the model is fitting the data well. So basically, this is the chi-square value, or the chi-square test value, the degrees of freedom for the analysis, and then the p-value associated with that. And so basically, a p-value conventionally less than or equal to 0.05 would indicate a significant chi-square value. And in the context of SEM, that's actually indicating that you have poor fit of the model to the data. So given that our p-value is greater than 0.05, this would actually be signaling that you have a good fit to the model, good fit of the model to the data. The one downside of this particular test is it is impacted by sample size, and so in really large samples, this could indicate statistical significance, which might lead you to the conclusion of a poor fitting model when the test may be just simply overpowered because of the sample size. So for that reason, the chi-square test is not often utilized alone. Generally, it's utilized in combination with various descriptive indices of model fit. So if we scroll down, you can see that these are various other fit statistics. We have the comparative fit index, and basically values that fall between say 0.9 and 1 would be indicating good model fit. Probably a more stringent standard would be a value of 0.95 or above. But the CFI values range between 0 and 1, and values above 0.9 would be considered good fit. Values above 0.95 might be considered, very good fit. The Tucker-Lewis index also generally is going to range between 0 and 1. Sometimes it can exceed 1 by a little bit. And with the same general conventions that I was just listing for the CFI, which is the comparative fit index. So this is a comparative fit index and the Tucker-Lewis index. If we scroll down, we get the RMSEA, which is the root mean square error of approximation. And basically, a good fitting model would have values that would be at or below about 0.05 or 0.06. Values up to 0.08 would be considered acceptable, but 0 is the lowest value that you can get with the RMSEA. So this would also be signaling that we have good fit. So we have an RMSEA value that's 0. We have a comparative fit index of 1, Tucker-Lewis of 1.083, which again, these are indicating good fit. So those are just a couple of fit statistics associated with SEM that are utilized in order to address the question of model fit. But again, you also have some other issue, which is the parameters in the model, what's statistically significant, and so forth. You can see that this path right here was not statistically significant. So it might be the case that you feel like modifying this model by removing that path or whatever, that could conceivably improve the overall model fit to the data. The one downside of making modifications after looking at the overall fit is that you then run the risk of capitalizing on chance. So if you are going to make any kind of modifications, it's important that you present your hypothesized model first, run the analysis, evaluate fit, and then make whatever modifications, and then be explicit about what the modifications are, and and any justification that you're using in order to make those changes. So that pretty well concludes this introductory overview of using AMOS with regression analysis and path analysis. There's a lot more detail. There are a lot more details that we could go into, but this was just to kind of give you an overview of how to use the graphical user interface and how to import data into the program and run the basic analyses.